Hi everyone, and welcome to a new episode of the Allplane Podcast, where we talk with the movers and shakers that are redefining the future of commercial aviation. As usual, before we get into today's episode, I would like to remind you that all previous episodes of this podcast, as well as many other aviation stories, are available on the Allplane website. That's Allplane.tv, Allplane.tv. And I also would like to use this opportunity to invite you to subscribe to the Allplane newsletter about innovation and sustainability in the commercial aviation industry. So go to the Allplane website and there you will find a link to subscribe to the newsletter. And now to today's episode. Today's guest is Ivar Aune, CEO and chairman at SiriNor, a startup that is working on a particularly interesting approach to electric propulsion. There are quite a few companies out there that are working on electric aircraft, but most of them are basically using electricity to run some type of propeller. However, SiriNor, and this is what I found truly interesting and a bit intriguing to be honest, is trying to run a jet engine on electricity. How is this possible? Well, I won't make any spoilers yet, so you will have to listen to the conversation. But let's say that the engine that SiriNor is working on, and that has already been tested successfully on the ground, is expected to deliver significant improvements over traditional technology, over traditional jet engine technology, and not just on the environmental front. It could also be cheaper and more performing than conventional jet engines. And what's more, the uses of this electric jet engine won't be restricted to the smaller categories of aircraft, like so many other electric aircraft that are currently under development. Ivar and his team aim to develop an engine that could potentially power larger airliners, like the A320, Boeing 737 size of aircraft. So if you're like me and hadn't heard that much about this type of electric jet engine until now, don't be surprised, because SiriNor has been working pretty much under the radar all this time, the last 4 or 5 years. I hope this conversation will offer an interesting glimpse into what is a truly promising technology. So I think it's best if, without further ado, I welcome Ivar to the podcast. Hello Ivar, how are you?
I'm good, thanks. How are you, Mikko?
Very good. Thank you very much for joining us from beautiful Norway.
Well, thank you for having me. I've looked at the caliber of your previous guests and I'm hoping I can match them, but we'll find out.
I'm sure you will, because you are leading a pretty ambitious project.
Yeah, I am.
Let me give our audience a couple of lines as an introduction. You are the founder and CEO of SiriNor, which is a company doing an electric jet engine, which sounds very intriguing because normally we don't associate electric propulsion technology with jet propulsion technology. So I'm just full of questions that I'm going to ask you now. And also about where are you with this project. But before that, I would suggest if you could please give us a bit of a background about yourself. I think you come from the oil industry, is that right? And you've been also in investment, finance.
Yeah, that's correct. I'm actually not one of the original founders of the company.
Okay. But you are the CEO at the moment, yeah? CEO and president?
Yes.
Okay.
CEO and chairman of the board of SiriNor. So as you said, I'm based in Stavanger, which is on the southwest coast of Norway. Traditionally, Stavanger is the energy hub of Norway, but it's also going to be an important hub for electric aviation. So already from August, September, Bristow, Norway, which is a subsidiary of the Bristow Group, will start flying between Stavanger and Bergen with a Beta Technologies aircraft. So it will be a test flight. They will fly up and down the coast with it just to test the implications of electric aviation and see how it works.
Nice. We've got a few guests from Norway here on the podcast. From the the airport operator, Avinor, also Elfly, the electric seaplane company. Well. Obviously it's one of the hubs of clean technology in general, but particularly in aviation. It's a country that I think is punching above its weight when it comes to advancing the clean aviation agenda, I would say.
I hope so. But I graduated with an MSc, a Master of Science degree in petroleum engineering. So I come from the dark side. So I graduated in 1997 and went to work with an oil company here in Norway, first as an engineer. And then after about 10 years of working in operations around the world, I transitioned to business development, still within the oil company. And after a few years, I went from business development to corporate venture capital. And I was there for about 8 years. as an investment director. So I did close to 30 transactions, mainly in upstream energy, but also in medtech, fusion, and in hydrogen. Crucially, I led the hydrogen investment team. So I think if I can mention two investments, I was part of Swedish Medfield Diagnostics and Boston-based Commonwealth Fusion Systems are probably the two that I'm most proud of. When it comes to SiriNor, though, the actual founders, there are two of them. So one is a Norwegian, his name is Lars Robertson, and the other one is an American, Abhijit Inamdar. So the two of them came together back in 2020. And they had a shared dream of making aviation not only faster, but also greener. So Lars is the creative mind who kicked off this development. He's a curious guy. He's a serial founder who loves engines. And I think this to him was the ultimate challenge. He wanted to build the best jet engine in the world, one that could even power supersonic aircraft. Abhijit, on the other hand, he came from the same venture team that I was working in. So he and I had been working together for years. And it was he who eventually reached out to me and brought me on board. So we both left. It was Equinor Ventures we were part of. He was in the Houston team. I was here in Stavanger. He left in 2020. I resigned in 2021, and then we came together again in SiriNor. So for me, it was sort of I felt like in 21 that I'd reached a crossroads of my own. Like I felt that I was living in a fossil fuel social bubble or echo chamber, and that my motivation and my aspirations didn't any longer match the strategy of the company, right, or the industry. So I was frustrated by the slow pace of change in the energy sector. That's why I stepped away from my role there. And I wanted to work in a smaller team, with shorter communication lines, less red tapes, where you really can drive innovation. So initially, I worked both as a consultant for private equity fund Verdane and for SiriNor in an advisory capacity, but I couldn't do both at the same time, and I was drawn to SiriNor by the possibility of contributing to something meaningful here, which is sustainable revolution in aviation.
Yeah, you pointed out something which is very interesting, very paradoxical, is that Norway is one of the leaders in clean technology, but at the same time, it's deriving a big chunk of its wealth from fossil fuels and oil and gas, particularly.
Absolutely. And I'm not sure we have that we are well prepared for the transition that will come, because so much of our income relies on oil and gas still. I think it's like 50% of our industry.
And you mentioned fusion. Are you referring to nuclear fusion, or what type of fusion?
Yeah, absolutely. Yeah. So I was part of a team that made an investment in a fusion technology company in Boston called Commonwealth Fusion Systems. They're one of the leading companies in the segment, and I'm hopeful we will see their tokamak operating middle of next decade commercially on a test level, and then gradually expand globally. Because if we can make fusion work, it will disrupt everything. So that's super exciting to follow.
So that would mean basically an end to energy scarcity. Yeah, it would be
hopefully and contribute to equality globally. And that's also something we're working on in SiriNor, because we're looking at like the future of aviation. What will happen if a global CO2 tax is applied to tickets? Will the majority of the population still be able to enjoy the massive benefits of aviation? It's a question we're asking, because aviation is beautiful, isn't it?
It is,
nothing like it connects people around the planet. It's the fastest, most reliable and efficient way of transporting people and goods around the planet. And we don't want that to end. But at the same time, it comes with a massive cost, a massive negative externality because of its contributions to climate change. If it wasn't for that, aviation has the potential, I would say, to become our most environmentally friendly mode of mass transportation, because we use so little land area. That's one of the fortes of aviation. Our physical footprint is really, really small. We don't like cars need these roads, these wide lanes of tarmac plowing through mountains and forests. Railroads do the same, disturbing wildlife, breaking up natural habitats. In aviation, we don't do that. A small
Hmm.
footprint here, a small footprint there, and an aircraft to take us from A to B. So we need to come up with a way of continuing to benefit from aviation, making it available to everyone, but without the disruptive effect on climate and nature.
Yeah, indeed. Yeah, I just got curious about when I heard the word fusion, because I mean I'm broadly speaking familiar with what it involves, but I don't claim to be any expert in that, and I haven't been really following what's going on in that scene. But I didn't even know there was an investable case
No, yeah,
for energy for fusion, for nuclear fusion. Well, that's gonna
absolutely, there is. Yeah.
interesting. I'm just making a note here to make sure after this conversation to go check what's going on in that space, because that's truly fascinating. Very good. So getting back to SiriNor and a new project. So basically you are designing an electric jet engine. So just going to start with the basics. How does it work? Because we usually tend to associate electric propulsion with other types of propulsion. Other types are like propeller spin or something like that. Tell me more about this, about the electric jet engine.
Well, let's start with something. I don't want to sound patronizing here, but let's start with electric turboprops because I think
Mm-hmm.
it's easier to explain. So to make an electric turboprop or propeller work, you basically connect an energy source like batteries or hydrogen fuel cell to an electric motor. That electric motor spins and it's connected to a drive shaft, which also spins. And that drive shaft is connected to the hub of the propeller. So everything spins. The motor, the drive shaft, the propeller, everything spins. Very simple. For an
Yeah.
electric jet engine, it's difficult to get to the thrust levels you want with that basic design because you have to operate within the confinement of the cowling, right?
Mm-hmm.
So unless you want to make the fan diameter extremely large, you're struggling to produce a useful thrust.
Yeah.
But the right way to turn a propeller is not to rotate it at the hub. It's to apply a force at the tip of the turbine blade, at the tip of the fan. So that is what we do.
Okay.
Um, Around the circumference of the engine, we have a series of small electric motors. Each of them drive a small compressor. And
Okay.
the air that comes out of those compressors is directed onto the tip of a tip turbine fan. And that is what makes the fan rotate. And by not rotating it at the hub, but instead rotating it with a pressure applied to the tip of the fan, we can use 20-30% less energy to rotate the fan. And that
Okay.
means that we can get the kind of thrust levels you would expect from an engine without having to increase its diameter. So if you're looking at say a 2-meter fan, one
Mm-hmm.
that you would find on an A320 or a Boeing 737, so the typical
Mm-hmm.
medium haul aircraft.
Yeah.
Our engine of a similar size has a target output of 90 kilonewtons. So we're right in the lower range of what the combustion engines on mid-range aircraft can output. And I think we can probably squeeze more out of our design once we've tested it more and learned more about it. But that's sort of what we're looking at.
Mm-hmm. When you say
We
20 to 30% less compared to what exactly?
to rotating at the hub.
Okay. And this engine, potentially, you could power any type of aircraft, adjusting by size?
That's the beauty of it. So we can use basically the same core technology,
Uh-huh.
but just increase the diameter of the fan. So we can build it really small, like 30 centimeter diameter, with a target output of 1 kilonewton of thrust. So that would be ideal for your drones, your unmanned aerial vehicles.
Mm-hmm.
A 1 meter diameter fan would be ideal for like a ground effect vehicle. We have two partners in that segment, Leviathan Air in Austin and Sea Cheetah in Florida.
Mm.
And then a 2 meter and above will suit larger aircraft, whether it's a private jet, corporate jet, or even a medium haul aircraft. And I think we can do even more, but we're not pitching that. We're saying that we will be disruptive up to the medium haul segment. And I think we shouldn't promise more than we know we can deliver. But I mean, when you're looking at a 3 meter diameter fan, putting it under the wing would severely limit the type of aircraft that you could fly because you would be dragging it along the ground. Right?
Mm-hmm.
But if you're looking at a blended wing body where you have the engines on top of the aircraft, maybe you could increase the fan diameter to 3 meter, and then we're looking at 250 kilonewton of thrust. So you can see that, but by scaling up the engine, the thrust output increases dramatically, and that's because of our core design. The way we make the fan rotate by applying force at the tip of the turbine rather than at the hub.
Okay, so you make it rotate differently, but the basic, let's say, architecture of the engine, the way it looks, just to to put it plainly,
On
would
the
be more
outside,
or
it
less the
looks
same. Uh-huh.
exactly like any other engine.
Yeah.
And the key principle, the delta pressure across the length of the engine, that is the same for a combustion engine or for an electric engine, right?
Mm-hmm.
It's the compression of air as it passes through the engine and is ejected at the rear end of the engine. That is what drives the aircraft forward, and we're achieving the same, but we're doing it without compression.
And
Without combustion.
and this would be enclosed by a nacelle, I guess.
Yes, exactly.
Yeah.
Yes.
Okay. And what about the source of electricity? How are you going to
So we're
store that or
completely
generate that?
yeah. So we're energy source agnostic. We are only developing the electric jet engine itself. We leave
Mm-hmm.
it to others to develop batteries, hydrogen fuel cells, or whatever. So we can be powered by either. Batteries would work fine for a UAV, a drone.
Mm-hmm.
If you're looking for range, then probably hydrogen fuel cells with liquefied hydrogen is the best way to go for now. What the future will bring, it's hard to tell. But we're there, we just plug it in and off you go. Completely energy source agnostic.
Mm-hmm. But if you
And in saying that,
yeah.
we're developing an engine that can be used both for retrofit and for new builds. But of course,
Okay.
retrofitting has its disadvantages. I know you've spoken with Val at ZeroAvia. They're doing retrofits with their
Yeah.
turboprops and hydrogen fuel cells.
Yeah.
Um, because for conventional combustion engines, you store the jet fuel in the wings, right? But once you move to hydrogen, you need to move the fuel into cylindrical tanks and probably store them within the fuselage. So when
Mm-hmm.
you're retrofitting, you are going to have to make some compromises and probably reduce your passenger capacity in it. So how much reduction in passenger capacity you're looking at will depend on the type of aircraft you want to retrofit, but a ballpark figure is 20% reduction in passenger capacity when you retrofit an aircraft. So, of course, designing from electric propulsion from scratch will optimize your aircraft design and make electric aviation far more attractive, I think.
Mm-hmm. So, but then if you are aiming for this, let's say, mid-size market,
Mm,
from when you told me, if you go with a battery electric, you will still have a problem with the capacity, the energy density of the batteries, right? The range and the
yeah,
weight of the batteries. If you go
yeah.
the hydrogen route, if you install some sort of hydrogen storage system, I guess
Mm.
maybe liquid, then wouldn't it be more efficient to just burn this hydrogen directly? Like there was this Airbus project to do an aircraft that was doing just that instead of
Mm.
installing an engine that like yours that is driven by
Yeah.
electric power, but at the same time you are installing the whole hydrogen system as well in
Mm.
the craft.
Do you mind if I take the scenic route when I answer that question?
Of course, go
So,
for it.
so what we're saying is our technology matters because today aviation has no scalable solution for reducing emissions. So that's a bold statement. So if I unpack that for you, beginning with the scalability issue. So we all know that fuel is a bottleneck for green transition, whether we're talking about biofuel, synfuel, hydrogen. We're concerned that these alternative fuels may not scale. But we mustn't forget that the propulsion system itself is also a bottleneck. And the reason for that is combustion. Whether you're combusting hydrogen or jet fuel or biofuel or synfuel, it would be the same thing. Because combustion means operating in extreme conditions. Jet engines, which make up about 70% of the aircraft engine market, they work in extreme conditions, particularly in the turbine section, where temperatures can exceed 1500 degrees centigrade. That's 2,700 roughly Fahrenheit for any American listeners. So that's hotter than the melting point of most metals. So to account for this, engine manufacturing companies rely on specialized materials, nickel-based superalloys, thermal barrier coatings, and other advanced materials. And there are multiple issues with that, with the use of combustion. Firstly, these materials, these specialized materials, they require proprietary processes, and they're subject to very tight quality controls. Secondly, there are relatively few producers of superalloys globally. So you're looking at quite a fragile supply chain and a tightly controlled supply chain. And lastly, these materials are often considered to be strategic assets, which means they're subject to export control and national security restrictions. And the result of all of this is that materials science is a key barrier to entry into jet engine manufacturing. So we're looking at a market known for its extremely high technical barriers to entry, regulatory complexity, long development cycles, and the reliance on a fragile supply chain of tightly controlled materials. The result of this is that the manufacturing of jet engines is controlled by a global oligopoly consisting of just a handful of players. The three main ones are GE Aerospace, Rolls-Royce, Pratt & Whitney. And indeed, most full engine design and certification is done in just 3 countries, the US, UK, and France. There are other countries that collaborate or supply components, but only a handful have this end-to-end capability. So that makes it extremely hard to manufacture engines, even for hydrogen combustion. So to resolve all of these issues, what we offer is an engine that is electric. And because it is electric, it operates at much lower temperatures. We call this the cool revolution. And that means that we can use standard aerospace grade materials, aluminium, steel, titanium, and standard CNC machining throughout. We can even use additive manufacturing for almost all engine parts. All of this results in a number of positive strategic implications. First of all, the cost to build our engines is much, much lower than any combustion engine. So it will vary depending on engine size, but if I say 30% reduction in cost as a ballpark figure, I know I'm not lying. Also, the operating cost, which airlines are very preoccupied with, will reduce considerably because of easier maintenance and fewer parts to replace. So it's hard to quantify exactly how much before we've seen our engines in operation for some time. But we have an example, which is the automotive industry, where electric cars have been replacing internal combustion engine cars for quite a few years now. And we know that the cost of maintenance for EVs is 40 to 50% lower than for ICE cars.
Your engine uses less parts than conventional.
Yeah, far less parts, far less material, and cheaper material.
Okay.
It also means that we can do faster prototyping, faster iteration cycles, because we don't need to buy all these expensive materials. And crucially, it means geographic flexibility in sourcing and manufacturing. We're democratizing the engine market. Now you can produce jet engines in India, in Norway, in Barcelona, where you are, because the materials are easy to get hold of, and anybody can do it with a standard CNC park or metal 3D printing capacity. You can produce these engines. So these advantages, they represent a fundamental architectural shift in aviation. So we're not just building a cleaner and cheaper engine, we're redesigning the entire industrial logic of how engines are built and certified.
And why no one has done it before? Because obviously
Because nobody has asked them to do it. Okay, so independent of sector, disruptive technology tends to come from startups. Large companies are amazingly good at incremental disruption.
Mhm,
Rolls-Royce, GE, Aerospace, Safran, Pratt& Whitney, they are fantastic in improving the efficiency of combustion engines, and they have done a tremendous job since jet engines were first introduced.
mhm.
But they're not set up for a fundamental disruptive change. Large organizations aren't. So that's where it comes from us, from a startup. And we're not the only one. There are many, many startups developing electric propulsion solutions for aviation. Most of them are focusing on turboprop
Yeah.
propellers because that makes sense, because you want to start small. But there are also like 4 or 5 of us who are doing electric jet engines, and we think ours is the most efficient, but it's a bold claim, and
Is it is it
I'll
a
have to prove it.
is it a patented technology?
It absolutely is. Yeah, yeah,
Uh-huh.
it is. We have applied for 2 PCT applications. Those have been approved back in 2023, and we had our first US patent approved in December last year. But let me
Mm-hmm.
talk about emissions, because you asked about
Sure.
hydrogen combustion. So
Yeah.
again, our enemy is combustion. So we all know that aviation needs to cut its emissions mainly due to global warming. You know, we've all heard the numbers. It's about 1 billion tons of CO2 each year. But what is often overlooked is that the actual climate footprint of aviation is 2 to 4 times that of its CO2 emissions when you factor in all of the non-CO2 effects on climate. So NOx, water vapor, soot,
Mhm.
contrails, all of which are a product of what? Combustion. And this is a key message from this conversation. It doesn't matter what you combust, whether it's jet fuel, syn fuel, biofuel, hydrogen, combustion equals climate emissions.
Mhm. Yeah.
So while the focus is on decarbonization and climate, there are other emissions as well from jet engines. So pollutants, for instance, which is an issue in and around airports, NOx, carbon monoxide, particulate matter, volatile organic compounds, all of these things make it a health hazard to live and work in an airport environment.
Mhm.
And the third one is noise, a massive issue near airports. I live 15 minutes from Sola Airport, Stavanger, and I wake up every morning at 6 o'clock when the first flights take off, because they're at 120 decibels right at takeoff.
Yeah.
We will operate at 70, 80, perhaps. So we're talking the noise level of a vacuum cleaner or a lawnmower or a cafeteria with a bit of background noise. So that is
Mhm.
what we want to achieve. So if we want to get to grips with all of these things, the global issue of greenhouse gas emissions, the local issue of pollutants, and the local issue of noise, you need to go electric.
Mhm. And
And
you
that is why
say
so many startups are focusing on electric propulsion.
you also claim that you are able to fly faster per unit of energy, I guess. What can you tell me about that?
So our first patented engine concept was an engine for supersonic aviation, an
Okay.
electric engine for supersonic aviation. So the cruising speed for that would be 1.6 Mach. For our conventional engines, you're looking at cruising speeds of about 900 kilometers an hour. So slightly, but not significantly above the cruising speed you expect from a traditional conventional commercial aircraft.
Yeah, I guess. I mean, you always will have the kind of regulatory issues as well if you approach the supersonic speeds because of the boom. But
Absolutely.
but is this because your engine is also, besides the environmental benefits, is it because it's more performing as well? So you could potentially build a supersonic airliner then with this technology.
And indeed, we have pitched it to the leaders I should say, the future leaders in supersonic aviation, so
Okay.
Boom, Spike, those American companies. But for now, they're working on their own conventional combustion concepts. But I don't think it will fly. I mean, you're
Mm.
looking at 6, 7 times the CO2 density of a commercial aircraft.
What
And in this climate, I don't think people will want to see that.
what about the military?
Yeah, so our technology is dual use. So we're looking at applications both for civilian and for military use.
Mm-hmm.
And we have there are some interesting aspects when you apply electric propulsion to, say, surveillance drone, for instance, whether that's for military or civilian purpose. But specifically for military, when you fly something, you want to make it as hard to detect as possible.
Mm-hmm.
So, of course, noise is an issue. We're handling that. The other big thing is thermal signature. And that's an issue when you're flying with a combustion engine operating at 1500 degrees centigrade. So what they do is typically they build a cowling around the engine to prevent any heat from escaping, which is not healthy for an engine. So after about 70 to 100 hours of operation, such an engine will no longer be efficient enough to fly. But if you go with an electric jet engine instead, we can theoretically fly for 5,000 hours. We're pitching 3,000, not to sound too positive. And that, of course, increases your operating expenditure massively.
And what's been the reception of the military people to this technology? I mean, I guess if there's someone that promises to provide all these benefits, I mean, they should be all over the place looking into it.
We've signed 7 MOUs or LOIs covering all the key markets: drones, UAVs, and eVTOLs, ground effect vehicles, and aviation. And we're open to signing more, of course. But as you said, we've been a bit quiet about what we're doing because we just recently did our technology readiness level 6 testing. We passed that milestone on the 22nd of March.
What does it mean?
And, you know,
I'm not familiar with...
Technology readiness level 6 is a ground test.
Yeah, I wanted to ask you about that. You did this ground test in April, I think, right?
March.
Yes.
March 22nd, yeah. So aviation is a very conservative business, and it should be. You know, we're transporting passengers up in the air, so we need to take safety seriously, and airlines do, and everyone who supply parts to aircraft and to airlines, they also take safety seriously. So, and that trickles down to the ones who invest in this segment as well. You know, the corporate venture arms of airlines and aircraft manufacturers, they typically don't invest until you have a working prototype, when you're at what they call a Series A investment. So we've been working hard to get to this point specifically, where we can show to the market, to potential investors, to future users, that we have a working prototype. Because so far we've been funded mainly through convertible notes from family and friends. And then in 2023, we took part in Shell's E4 accelerator, and Shell then invested in us. And then this year, just before we did the TRL-6 test, we also closed a round with Alok Shriram and Associates. So Alok is the senior managing director and CEO of DCM Shriram Industries, which is part of the Shriram Group. It's a 125-year-old Delhi-based conglomerate. So we have some money for now, but we're still raising. I mean, it's a continuous thing when you work for a startup. So we're trying to raise another $10 million by Q3 this year. And that money is intended to take us to first revenue. And we expect that to be in the UAV market with a 30 centimeter of diameter engine.
30 centimeter.
Yeah.
But I assume you would need hundreds of millions of dollars or euros if you want to...
Actually not, because we do not, for now at least, plan to build our own fabrics. We don't intend to manufacture our own engines. And several reasons for that. One is to keep the cost down for our investors. The other is when you build your own factory, you risk becoming your own bottleneck. So either you are optimistic and you build a too large facility and half your equipment is sat idle, or you're pessimistic and you build it too small and you cannot produce what the market expects. But also we want to take advantage of, and we have this flexibility because we are a small startup, we can pivot to wherever the market is. So if the Americans say you need to produce in the US, right, we can go and do that easily. We can outsource manufacturing to Americans. We can produce engines in Europe. We can produce them in India, in Southeast Asia, where traffic passenger numbers are projected to increase more than anywhere else.
And is there a market for let's say contract manufacturing for something as sophisticated as a
But
jet
that's the
engine?
thing. It's not that sophisticated. The design is actually quite simple, and as I said, we can do it all from standard alloys using standard CNC machining or additive manufacturing technology.
Okay.
But of course, the first prototypes we need to manufacture them with someone who has the license to manufacture and be certified for aviation.
Mm-hmm.
And indeed, we've set off 2 years for testing and certification for aviation. For the other
Okay.
segments, it's easier, like for UAV.
Yeah.
Depending on the risk profile of your flights, you may get away with an integrated system test instead of a full-scale engine test. For ground effect vehicles, although they fly a few meters above the surface of the water, they're typically classed as marine vessels. So
Yeah.
that also makes certification a bit simpler. But when we come to aviation, it's dictated by the FAA, the EASA, right? And we have to comply with those regulations. So we set off 2 years in our development plan for that. So we're saying we're ready for UAVs next year, ground effect vehicles as well. For aviation proper for aircraft, we're not rushing it. We've set off 2 years in our schedule. So we're looking at having a certified engine ready in 2029. So before the end of this decade.
Okay. And tell me about this test you conducted. So basically what you did is you fired an engine prototype on the ground, right?
Yeah. So we built a test bench in Pune in India. And in that test bench, we hung a prototype engine. It was 40, had a 40 centimeter fan, tip turbine fan, electric motors and compressors, and we connected all of it to a battery pack. We wanted to keep it as simple as possible because we're not testing the drivetrain, we're testing the engine only.
Mm-hmm.
And then we ran that several times, and we actually still have it up and running, and we can continue to do testing on it and modify it and test again. And we were targeting 40,000 RPM and achieved 60,000, if I remember correctly.
Okay.
And we also exceeded the thrust output of the engine. So we far surpassed our test objectives. It's only one step on the way to having a certified engine. So we're following NASA's technology readiness level system rigorously. So
Mm-hmm.
this was TRL 6, a ground test in a simulated environment. And then the next will be TRL 7, technology readiness level 7, which is a flight test, which we intend to do on a UAV, hopefully in Q3.
This year.
And that would, yeah, this year. And that would be completely different because when you do a TRL 6, you're only testing your own product. So you set your own test criteria and you test against those. But once we get to do a flight test, of course, we will be working together with battery providers and indeed the owner of the vehicle. So we will have to come together and define the test criteria, and it will be not just an engine test, but also a systems test.
Okay. Yeah.
After that, we should be ready to go to certification, which is a completely third-party certified test, where the external third party, whether that's FAA or EASA or someone else, sets the target criteria, and we are forced to meet or exceed them.
You're gonna get it certified where? In Europe, in the US?
It depends where the first user is. So one of our first customers is an Indian-based UAV developer. So that means certification in India as a first stage, and then we can expand from there.
Yeah, actually,
but of course,
sorry.
testing and certifying takes a lot of capital and a lot of resources, and we're a small team. We can't be expected to go for global certification right away. We have to do something that is fit for purpose.
Yeah, actually, you introduced a couple of topics. It's the next thing I wanted to ask you about. One of them is India, because you mentioned you tested this in India. I mean, you're based in Norway, but SiriNor is also an Indian company in a way, right? You have a big part of your team is in India, and shareholders are in India as well. Can you tell me more about this India connection?
Yeah. So when Lars decided he wanted to build an electric jet engine, the first engineer that he managed to convince was an Indian-based engineer, Pramod. So this was early 2020, and Pramod was hooked on the idea, and he's now our chief propulsion engineer. And we've built the team around him. So first in Bangalore in India, and recently we moved to Pune. Pune is a manufacturing hub in India, so it made sense for us to be there because we rely on the local supply chain to build the prototype. So the corporate structure is the parent entity is Norwegian, and that's where all of the IP belongs. And then we have an Indian subsidiary, and we do all of our engineering in India. And to date, we've done all of our testing in India as well. We are considering establishing a US-based entity, both for ease of attracting American-based investors, but also because with the recent trade wars and everything that happens, and some of our clients being in the US, it may be necessary to have a US-based entity. But as I said, we're a really small team. And to have a US entity, you need to have boots on the ground. So we would have to employ someone there. Yeah, I'm not sure it's the right timing yet. I think we're maybe a bit too thinly spread as we are. But so we definitely have the capability to, as I said, pivot to wherever the market is, move the team, move everything to wherever the customers are. Yeah.
How many of
that's one
you?
of the benefits. So we are, I think now we're 8 full-time. And around 18 altogether when you count interns, advisors, board members. Yeah.
And you come from, or you've been spending quite a significant part of your career in the world of finance. So from a financial, commercial perspective, what is the business plan here? Well, you mentioned you are looking to raise some further rounds of funding, but then what's the road to market? Is it to partner with one of the major OEMs, like Airbus, Boeing, etc., or is it to work with your own designs further into the future? What's the potential here to make it into the big leagues, into this kind of A320, Boeing 737 territory?
Yeah, so for now we're focusing on the smaller engines. So as I said, we're looking at certification of first sale in 2026, and by 2027, the hope is that we are operational both in the UAV market and in the ground effect vehicle market. And indeed, we have signed MOUs with several companies in these two segments. From there on, it will take us another 2 years to achieve certification for aircraft. While we're doing that, we hope to also expand globally in ground effect vehicle market and UAV market. So in order to get our engine onto an aircraft, we would have to align with somebody like ZeroAvia. I don't know if they still have a jet engine on their business plan, but they used to have one at least. So when they decide to expand from smaller aircraft where turboprops are ideal to larger aircraft that are heavier and designed to travel longer and faster, then they might need a jet engine, and then we're ready to supply it to them. Or we could talk to the two larger credible projects, Embraer's Energia project and Airbus's Zero E project. Unfortunately, they're moving a bit slower than we had hoped for. Airbus recently announced a decade-long postponement, I think, of Zero E, and we're talking to both of them, but for now, it doesn't really matter to us because we don't have a certified engine for those markets, and we're targeting these other markets meanwhile. But of course, we want to break our way into aviation, not only because that's where the big market is, but also because that's where the massive CO2 emissions, greenhouse gas emissions are. So that's what we've been wanting to tackle from day one, and that is and has always been our objective.
But I
So we're
guess,
actively looking for partners in those segments. We've signed an LOI with Flybird
yeah,
in
yeah,
Germany. He was on your podcast a couple of
correct,
weeks ago.
correct. Yes,
So
I
we
was
have an
about
LOI
to
with
mention
him.
it.
Yeah.
Hmm.
But of course we're actively looking for other partners in this segment and happy to
Hmm.
sign up MOUs with anyone who has a credible ambition of flying electric in the future.
Yeah, indeed. I guess even if without the environmental component, if you are able to deliver a lower cost and
Mm.
improve performance, I guess in itself it's already a strong business case.
Sure, but I mean, in aviation,
There's the inertia, of course. There is
yeah,
the the difficulty of changing the way things are done, right?
it's a conservative industry.
Yeah.
Aircraft are designed to last for 20 years, so you have that lifetime cycle
Hmm.
to consider. Actually, if we look into the future, bring out our crystal ball and try to
Hmm.
imagine what the future will bring. We don't need to look that far into time, at least if you think of time in the context of a life cycle of a typical aircraft. But what we will see is that aviation will be facing the inevitable end of the fossil fuel era. I'm saying this as someone who has spent 23 years in an oil company. Like the end of fossil fuels is not happening this decade and probably not in the next decade. But the warning lights are already blinking, and aviation needs to take that into account. For instance, did you know that new fossil electricity capacity peaked in 2010 already?
Okay.
Or that
Didn't know.
oil and gas capital expenditure peaked in 2014? That internal combustion engines car sales peaked in 2017? And also fossil fuel demand peaked for industry in 2014, for buildings in 2018, and it will peak for transportation as well. Transportation lags virtually all other sectors in the green transition.
Hmm.
And World Economic Forum has predicted that unless aviation takes decisive action, our industry may end up being responsible for as much as 22% of anthropogenic CO2 emissions by 2050.
Hmm.
And that's largely a factor of all other industries managing their emissions while aviation fails to do so. So can you
Yeah.
imagine the scrutiny that our industry will come under if that happens? You know, the flight shaming that we see today will be nothing compared to what we will see under such a scenario. But there are some positives, though, to being a laggard, because
Hmm.
we have the benefit of learning from these other segments.
Hmm.
And one very important lesson is that the growth of key technologies, examples could be solar, EV, batteries, the
Hmm.
growth of these technologies has outpaced outpaced all forecasts, and the incumbents in these segments have completely underestimated the actual rate of transition.
True.
And I won't
Yeah.
be surprised if that happens in aviation as well. In fact, I expect it to. So there's a green disruption,
Hmm.
and it's about to hit transition, including aviation, the same way it has done in other segments. And the predictably slow response from the incumbents is already creating market opportunities for new players, such
Hmm.
as us who are developing electric jet engines, for ZeroAvia, for developers of aircraft designed for electric propulsion, for
Hmm.
Flybird, for airlines, startups that are focusing entirely on electric propulsion from day one. So that
Yeah.
is the future, the way I see it. So our product is an electric jet engine with zero emissions. It's a compressor, basically, air in, air out. And because it's electric, it's future proof. It's built to survive the green transition. And
Yeah.
that is
Interesting
our
times.
ambition. Yeah, it is big change to come,
Hmm.
but I think we'll be ready for it.
And if people wish to learn more about your company, where should they go? Because you've been pretty secretive,
Yeah.
keeping a bit behind,
Uh,
like under the radar. Even
yeah.
when I was doing research for this podcast, it was hard for me to find some information that they're out in the open.
Yeah, no.
So, how can people track progress you are making?
So our website is not very informative, but it's a starting point. There are also a couple of links there. One is you can sign up to our newsletter. It doesn't come out very often. We respect people's time, but it's one way to receive information as and when things happen. There's also an email address, contact@sirinor.com, where people can reach out to us and ask about anything. anything they want to ask us. We're quite open now that our technology is patented. We don't have to be so secretive anymore. So we're open to discussing how our engine may suit people's needs, or to discuss our next funding round or partnerships of any kind. So please reach out, and we'll be able to accommodate you.
Perfect. Well, thank you so much, Ivar, for the time today. It's been really fascinating to learn about this new technology that even if I'm following this industry quite closely, I was relatively unaware until quite recently. I get your email send-outs, but of course, because as we were mentioning, you've been keeping it a bit under blankets. It was hard to guess exactly what it was all about. So thank you so much for coming on today here on the podcast to talk about it, and wishing you all the best with this venture. It sounds very promising.
Thank you so much. It's been a huge pleasure to speak to you today, Mikael, and I'm happy to come back again once we have something new to report.
Let's do that. Thank you very much. If you like this podcast, you can support us by giving it a great rating on Apple, Spotify, or whichever platform you get it from. And remember, you can of course subscribe to it. And you can also get regular updates through the Allplane website. That's Allplane.tv. We have a newsletter where we cover the aviation industry every week with a special focus on innovation and sustainability. So give it a go. Thank you and goodbye.